respected sir, and hello friends. We Manish Bajpayee and Subhas are presenting the term paper presenting the complexity of the evaluating game trees. Here we will discuss the what is the game and what is the game tree. How do these game trees problem can be solved using the some algorithms, Minimax algorithm and the alpha beta algorithm. Then we proceed to the parallelization of these algorithms. Here we will introduce two types of problems where the game trees have the real values in their leaves, and in second where the boolean values are stored in the leaves. Then we will discuss the complexity of the problem and the network model which are appropriate for these algorithms. First is what is the games. Game provides the environment for the pure competitions among the two agents or two or more than agents, and game is the purely intelligent human activity, and no doubt it provides the fun to us. Mainly we are discussing about two types of games where we have the perfect information about the game, what the options and what will the result. And in another case we are discussing about the games where we have no problems. In the games where we have the perfect information, there is nothing but it's something searching problems.
In this slide, we all after this we are giving emphasis on two players game. All the game trees are made for two players game. For solving two players game, here in game trees we need perfect information. Means we need the information of nodes of leaves. That maybe for any games, the games for games tree in any game there are 5 things: states, which he is making in bold, operators, initial moves, goal, and payoff function.
So this is the initial state, which is the board configuration initially. If we take a one move, this is the legal move, which is known as the operator, and second one is the goal. Goal is the winning configuration, how we take the moves to win this game. And what is the remaining states? This is the board configuration. All these states are the board configurations.
And goal is for both players. One is for winning, one is losing. Here it is game how the game trees are made. This is for a two-player game. One is computer, one is opponent or user. This can be changed in anywhere. This is first ply of move. First ply means one move is made of two plies. Oh yeah, in this slide it is clear. For example, this is tic-tac-toe game. Here this is first ply where he made cross, and the second ply which is played by second opponent player, that is he is giving 0, and this is one move. One move is consist of two plies. In game trees also the same thing, means one is root, and after every consecutive things there is one ply. Game trees representation of any problem by a tree, any game problem by a tree is called game tree. A node represent board position, for example these positions. Root node is the position in which decision must be made. Root node is the final position which says that which player wins. Evaluating function f. Evaluating functions evaluate of every node, and by evaluating nodes of child node, we calculate ancestors of that node, and finally we calculate what is the root node, which says that which player wins. This is the example of tic-tac-toe game. How they here it is win by.
This is the.
This is winning. How this is winning? Yeah. I think 1 minute.
The next one is the which one?
Next one, yeah. Here it is winning for the node, and this is simple, we know. And good move for that one, because here it is winning nodes. this can't be a good move because the chance of lose is here.
No, whatever.
Hmm?
Just for curiosity.
Yeah. Actually, this is
No, whatever you told that this cannot be a good move.
because here is chance of lose. Here.
He has won, right?
No. One is for 0, but cross is loses the game. 0 is opponent's move.
One, 0 is opponent.
Yeah. So here it is chance.
But if 0 is opponent, then that one also.
No. Here the chance is this.
Why prior to that?
One minute.
Prior to that step, he has already won.
Here he did cross, and then here he loses. One minute. Here he loses.
Here loses, no problem. There is
And
one
here. Is there some problem? Yeah, actually, there is some mistake in making slides. Actually,
The last one is
yeah, this is it may be possible that this is not so important because we are making in games. General min-max processor. In this game, in general min-max, there is also a min-max theorem which says that min-maxing and max minimizing are both same. But we are not going in that thing. We are saying we are making a processor. This is min-max. For example, it is maximizing. This is minimizing mode. This is maximizing mode. Then it tries the maximum value of all three, and this is minimizing mode. So it tries minimum value of all that. And final output is the value of root. If it is some threshold value, in most example that is 0, where there is negative and positive both value. Says that same thing which we said that low numbers is for opponent and high numbers is for the first player. That here it is said that what is the complexity of min-max in general, because the main aim is to reduce the complexity of evaluating game tree. The general complexity of min-max tree is b to the power m time complexity. That is very much because in this example the game tree is very short, but in general that is very large because in tic-tac-toe example the game tree size is the number of nodes is 128. So you can think that how much large, for example in chess that may be in millions because tic-tac-toe is so simple game. So b to the power m is b is here depth, b is the degree and d is the depth. And this comes because we have to calculate all degree for calculating root nodes. We have to evaluate all degree and then calculate this, and after that again it comes b into b up to the left.
See, it's okay. In the worst case scenario is okay.
Yes.
In some cases, the tree will not move.
Some cases in tree will not move.
For example, that is a case of no decision will be arriving, right?
No decision means there is he can't evaluate which is good,
No, nobody will win the game.
Nobody
will win the game.
Sir,
so the tree will stop there. You cannot go further.
No, actually here means only two player are gaming, and nobody is.
Say in the chessboard, sometime that both of them are realizing that this will not lead to any decision.
Yeah, that
Right,
comes
and
root.
that is
That
the
root
draw
node is
condition.
0. Means if we are giving negative value to the opponent and positive value to the player, then the evaluation of root node is 0. The evaluation can be done. Yeah, the performance will depend upon the evaluation function. How we evaluate the nodes. This is also important. Although we are not going in this thing that how we evaluate. Yeah, then we comes that this is b to the power d is very much. So what we decided what we did in alpha beta pruning, if you know that that this node is maximum value, then we need not calculate all those nodes. And in this, if you know that this node is minimum, then we need not calculate all other nodes. So these all nodes are pruned. This thing called alpha beta pruning, although we extend this idea in our parallel algorithm also. Yeah, for algorithmic alpha beta pruning, because we need in computer science everything should be algorithmic. We did value infinity and minus infinity to the maximizing node and minimizing node and maximizing node both, and we compare with the nodes. For example, this is minus infinity. If it is 5, because 5 is greater than minus infinity, so it goes to there. And if any other nodes, if you know that these nodes are less than 5, then we need not to calculate this. We also use, this is the algorithm. We at first give all nodes. Here it is minus infinity, infinity, minus infinity, infinity. Here it is 5, because 5 is greater than minus infinity, so the value of node is 5. Now this goes to, means this is now for pruning number for alpha beta. Now next slide. Here it is 2, because it tries to maximizing the things. It knows that 5 comes, so if it comes 2, there is no need to he has to maximize this thing, and he knows that 5 is there, so so the information of 2 is nothing, because if here 2 comes, this is nothing, means that information is useless. So we need not use these information. We also know 5. So after that, these nodes are pruned. All nodes are pruned. Now here it is 5. So 5 is stored here. And now calculate. If now here the thing is opposite, because it wants to minimize the node. So if any number is greater than 5,
Less than.
here it is less than, so pruned. Here any greater than 5, then it is pruned. Means less than 5 it is used, but greater than 5, then it is pruned. For example, it is 13. It goes here. It comes 13 after 5. Then 5 is pruned number for this, and again the slide is working. Then I think parallel algorithm are more important. Yeah.
So we are talking about the parallel algorithm. Here we take few assumptions. What is the we take the lower.
One thing I want to take. What is the problem in means why not any good parallel algorithm comes for game tree? Because if you are at first, there are many algorithms for parallelizing. If you know only Minimax algorithm, then we divide the game tree in many parts in many processor and they calculate. But because we have alpha beta pruning algorithm in sequential, therefore we can't make parallelize any algorithm because we need not see many nodes. We prune all nodes, and in parallel it can't. Although it is possible, but only for a. Although we are also trying to use alpha beta pruning.
So now we are talking about the parallel algorithm for the game trees which has the boolean values at their leaves nodes. Here we first make some assumption. First one is the pruning number. Pruning number is the number of leaves siblings of any ancestors nodes. Something like this, if this is a node. And here the pruning number of this node is 1. Then it means the number of left siblings of these ancestors. Any node is also ancestor of itself. So number of leaf subnodes of these nodes is the pruning number here. And leaf node is that node whose value cannot be determined from the nodes which is evaluated already. And the width is the if there is some leaves there and their value is something like this. We define a number w whose value let's 4. Then the nodes which has the value greater than 4 will be pruned. We only take in our consideration only these nodes. That is the width. The algorithm is first for algorithm we are taking the inputs at the NOR tree with pruning number and width. If pruning number is less than w, just put the sequential algorithm to solve any node. The sequential algorithm is if v is a leaf, then evaluate v, no, and if v is not a leaf, then there will be a leaf, their children u1, u2, u3. Take the NOR tree examples, recursively put, and the value of v we can be calculate. Then if it's 1, return 0, rather it's 1. So what are the number of processors used in this algorithm? If bit is 1, then the number of processor is n plus 1. This is very less number of processors. If width is greater than 2, then the number of processors lies between NCW to 2 times n to the power w. This is not 2nw, this is 2 times n to the power w. The complexity will dominated by the number of parallel steps in this algorithm. And number of parallel steps where AR is the number of parallel steps in which at most R leaves are evaluated in each step, and WET is the total work done. So this term will provide us the number of parallel steps in which minimum R leaves are evaluated. So this is the sum of parallel steps. That's why we are saying that this complexity is dominated by the parallel steps. So what is the cost? Cost will be the just complexity into the processor. What are the network models most suitable for this algorithm? In this algorithm we are dividing our whole problem into 2 subproblems, left subtree and right subtree. So we can communicate this part of information to neighbor processor. So put all the data in one processor. It will divide it into 2 subparts, left subtree and right subtree, and their neighbor processor will decide to do further decomposition of the problem. After all the processor have the leaves, they will evaluate the function and just pass the result to their neighbors. These are the references.
There was one reference, Kuhn's paper. Have you seen the Kuhn's paper?
Kuhn's paper?
H.T. Kuhn. On alpha beta, parallel alpha beta, pruning algorithm.
Actually, we searched in alpha beta parallel algorithm. One is SA, and one is Feldman, and
All the papers are
one is, oh yeah, it is written
all
here,
the-
all this, yeah. we read on this paper. But one thing is, means there is means not any paper provide what is the network model for solving this thing. Not means still no any paper. And we tried to do in mesh network because we thought that it can be solved. And we did, we calculate and our complexity is not improved, but because we made general situation, means
But the complexity will be improved if we are using the master and slave process. Then complexity will be definitely improved. But it's not. It's under research. Because in one paper
there are many means for example there is young brother weight concept for improving this thing, and few ones are extended this. We read, but we try to we not try means we included this thing as a case in our algorithm. So in our algorithm we are giving some cases and include all the means all the good algorithms.
Any question?
Any questions?
The tree model for the network. Tree model for the network?
No, in tree model actually we thought, but there is very less connection. We need less.
we need more connections. That's why we want to.
Because we have to keep the things, all the nodes. We also, one thing we also need to, means evaluation of this node, we have to tell the other, means siblings of ancestors, we have to tell. So tree model is, means we can't do in tree model. Means then it becomes as sequential and there is problem. We tried in tree model. Also we tried in hypercube tree model, and
You are going to tell us
Yes, sir.
what is the difference between your model and their model.
We'll compare the complexity and the cost. Yeah, we'll do that.
And your partner is here, opponent.
Opponent is missing. Yes.
That.
But sir, we have compared that thing, so we'll mention their complexity as well. So good morning everybody. Like the problem we did in our term paper was K-sort. So the outline of our presentation will be like we'll first define the problem. Then in the phase 1 we'll do like given an any array, we try to get the K-sort array. We'll suggest some sequential algorithms for that, parallel algorithms, and we'll do the time complexity analysis along with the problems. And in the phase 2 we'll also tell you one algorithm to do K-sort to full sort.
Why don't you notebook?
Okay, sir, I'll do that, but I'll be needing that. So the definition of K-sort is given any array with n elements.
Because this is a platform where your present, say, previous speakers, you observe the problem they face. There is no synchronization. Both the person wants to write or wants to speak. Right? So this is a happy. You have to be told, right? While you speak, generally you should not move it.
Okay, so yeah, no. So the definition of K-sort is like given any array with n elements, if an element is at the ith position in the sorted array, in the K-sort array, it should lie between the range I minus k to I plus k. So like the first sequential algorithm that we'll describe is like not a very tough one, but like it says for I ranging between this, we find like what we do is like given any array, we find the elements kth, 2kth, 3kth, the kth multiples of the and then partition along with that, like sequentially run through the array, and like the elements less than k are sorted kept over here and along with that. So the find I, what he does is will find its ith largest element along with partitioning array around it. So the time complexity for this algorithm will be n into n upon k plus 1. N into k plus 1 is the loop, it goes along that, and n time to prune through the array. So other algorithm will be the K-sort start and. In this what we do is we find like from the middle kth largest multiple, like near to kth largest multiple, and we partition along that and give the algorithm recursively from start to mid and mid to end. So did you understand?
So what you are doing, you are finding the middle value.
And mid, yeah.
Oh, and then you are calling again. Then it becomes. Is it not? It becomes a sorted element.
No, from near the middle element we find the kth multiple.
Right.
we'll do the mid is equal to the nearest kth multiple up or near to the middle element, and if there is no mid, that means like it is less than k, we leave that particular array as it is, otherwise we call this again. So the time complexity for this will be reduced, and it will now become like n into log n by k, because the number of recursions here, it becomes now log n by k, because we will call it. And then there is like KQ sort. What we do is like, this is a variant of quick sort, in which we do is like, whenever we have like a partition that has a length less than k, we leave that as it is. So it goes like, if n minus start is less than k, that is like a partition has a length less than k, we then leave it. Otherwise we find the median. We use median sort to find in this, and else it is like recursively calculated, the KQ sort. It is like very simple. So in this case,
in that case,
yes sir,
there are some positions where the element will go to his own position, right? There are some elements, because you are partitioning it.
yes,
So partitioning element will get his own position.
yeah,
Right? So suppose you have done, instead of x number of steps, you have done say 5 steps.
sir.
So 5 elements, at least 5 elements will get his own position.
Yes, sir.
Agree? Because you have partitioned. That means that these 5 elements, they are not satisfying your k sorting criteria.
No, so they'll be lying in a position in which like
If
the
the position is same.
So
Position is own position. Yes or no?
yeah.
Yes. So the 5 elements, so you have given more comparison.
yes.
You
But-
have spent more time.
We have to be sure, there is no way to be sure that exactly array is case sorted. Either partition length is
No, I'm trying to justify myself.
But in this case also like the complexity, the order.
Suppose instead of order n time or n minus 1 time
Sir.
for partitioning, suppose I do n minus 5.
then that element will be either plus 5 or minus 5, and then you can't be sure about next partition. That's the biggest problem. So you have to be sure from the first point partition element, last partition element, then you will be sure that partition length is exactly less than k.
To get to the
Otherwise,
final.
in your cases, the partition length will be k minus 5 to k plus 5. And that will be.
So in this particular case also like you claim the time complexity comes like this only, because like apart from the quick sort we do a less amount of work. So need I explain this thing like
No,
how
this
this is okay?
obvious quick your formula is using quick circle, but why log?
That was I was to say, like it will be like
n by
n
elements and k log k elements.
n log n minus the sum work that will not do. That will be like summation li log I, where the li represents the partition length that we have dropped out. So it will come out like minus, if we say like li to be represented as n into fi, where fi is the fraction, then we'll write it like this. We like we'll keep it like n fi log of n and minus this part. So this will come out to like n log n, and this will come as I'll write it here fi n fi log n fi
Log fi.
log fi, yeah. So it will come as log n into log fi to the power fi, summation of this. So this will come as n into log pi of fi.
So you have calculated. Let us show
Yeah. Okay, I will show that in the report. And then we can have like a randomized version of this particular thing, in which we start with an integer randomly chosen between the start and end. It is like this. So using these sequential algorithms, we try to suggest some parallel algorithms.
First, algorithm 1, we are going to propose 2 algorithms for parallel k-sort. In this algorithm, we assume that we have p number of processes and n number of elements in CREW PRAM model. Now, time complexity to find the median in n elements using p processor is order n by p log p. This can be explained as each processor will have n by p elements, and it can find its own median in order n by p time. And using P processor and the P medians that we found, we can find the median of that in log P time. Is the selection problem. And after finding the medians of medians, we partition around. After finding medians of medians, we call it as a median of the n elements, and the partition will be at least 25% to 75%. But okay.
Because you are using the partition.
Yeah, partition. Now total time to partition n elements around median is equal to first finding the median, and then partitioning will be done is comparing n by p processor. Comparing each processor will compare its n by p elements to the median, and then there will be summation of all these. Each processor will compare n by p elements to the median, and it will know how many lesser element or how many greater element will it will have, and then the linear doing the summation of how many lesser element it will have. Each processor can find its index in the partitioned array. Doing the summation in log p time. So it will require order n by p time. And given that p log p is less than n, that's the condition. Now the algorithm is quite simple. Find the median and partition around it, and recursively call the same function for both partition. With number of processor is distributed among that, means if the processor is before the partition, the processor will belong before the partition. If processor is on the intersection, it will have to do the work of both this intersection and that this partition and the other partition. And if the case is that the processor contains the n by p elements that the processor have contains the whole partition, then also the time required for finding the median and sorting around it will be bound by order n by p, because it's linear. Space complexity order n, that's okay. Time complexity will be order n by p log n by k, because each recursive step will require order n by p time, as we discussed earlier. And number of recursion will be order log n by k, because each time we will have at least 25%, 75% partition, and we will do that till the partition size is less than k. So time will be order n by k. So the number of recursion will be order of log n by k. Now the cost will be the time complexity is the same as the the time complexity is minimum when p value of p is largest, and the largest p value can be taken as n by log n, and in that case the best time complexity it comes out to be order log n into log n by k, which is same as the algo proposed by Satish. And cost is multiply time complexity by p, this will come as n into log n by k order, and it is better by factor log n from the algo proposed by Satish. And we are using the same CREW model. Now let us consider the case when we have EREW PRAM model.
Go back, what you are telling, the base time complexity is becoming log square and
Log n into log n by k. The time complexity is the same, sir, of same order.
But the cost.
This cost is less by or factor
We are
log n.
using more number of processors.
you are using?
N by log n number of processors,
And then using n.
and they are using n. So that log n factor comes. Now, in case instead of CREW model, we have EREW model, and for this case we will use a selection algorithm. Is given in paper reference number 1. That algorithm suggests that given n elements and n by log n number of processors, we can find k smallest element in order log n time. Is the constant on number of processors is there. Now algorithm is quite simple. Find the nearest k multiple of the center element, partition around it, divide the processor between partition, and recursively call the step one. It's approximately simpler. Instead of median, we are using k multiple of nearest k multiple of center element. Now the analysis. In case of we have m elements and p is equal to m by log n processors. Now time for step 1 will require that find the nearest k multiple of center element will be required order log m time as
Using m by log n process.
using m by log n is given, p is equal to m by log n. and time for step 2 is equal to similarly as I explained earlier, order n by p here, partitioning around the, it will come as m by p plus log m log p, which is still order log n. So the whole for each recursive step the time will be of order number of elements. So total time for n elements Tn is equal to order log n plus Tn by 2. So this is log n plus log n by 2 till log n power 2 n by 2 raised to power I, where I is log n by k. That means we leave the partition when the partition length is less than k. If we do this summation, it will comes out to be order of log nk into log n by k, which is still log n by k, because k value is bound by n. This time complexity is of same order as they proposed, and the cost comes out to be n by log. So the last thing is maximum number of processor which we needed for using that selection algorithm. We said the maximum number of processor needed for when the partition size is smallest, that is k, and number of partitions will be n by k. So n by k partitions, and into for each partitions k by log k number of processor will be needed for using selection algorithm. So total maximum number of processor will comes out to be n by log k. So the cost will be n by log k into time complexity, and it is still better by the factor of 1 by log k. Means it's still better by the factor of log k what they propose. And even we are using the EREW model. They were using CRE. That's all. These two are algorithms that we are going to propose. And next, sorting k-sorted array. Now, k-sorted array has a property that suppose in sorted array the element is at ith position. In k-sorted array it can be at max at I plus kth position. Now, element greater than I, that is I plus 1, can be at can be less than can be at max at I plus 1 minus kth position. So after distance 2k from any elements, all the elements remaining here are less than these elements, and similarly after distance 2k from any elements, all the elements remaining here will be greater than that element. So what we need to do only is the partition, choose any element. Okay, what we need to do is given an array, partition between the size of 4k, not partition, just take it as size, divided size of 4k elements, take any elements and partition around it. Take any elements, partition around it. Mostly choose a center element, because if you choose a center element, then the partition will be at max 25 to 75. And after partitioning, you will have the array like this. And each array will have the sorted, because this after partitioning, this is the largest element, this is the small element, and this will be greater than this, and this partition will be less than all other partition. Then sort among the partition. So maximum size of sorting partition will come out to be 6k. So the total time order is so time required for that is 6k log k, and total number of partition can be n by 4k. So order is n log k, and in sequential algorithm for the k sorting order comes to be n log n by k, and summing this it is approximate, it is order n log n for sorting the total array, but the certain factors will come, this factor, this multiplying factor, that is 3 by 2, that will come here, and we can't cancel exactly k, because we don't know exactly how much factor comes here. Doing this parallel is quite easy of GOH processor, 4k elements, and
you write this one very clearly.
Yes, sir. But there is second algorithm. For case sorting. Instead of doing partition and then sorting, just sort for each 4 elements, and for last 2 elements of this partition and first 2 elements of next partition, merge them.
Last 2 elements?
Last 2 elements
Last half and first half.
Acha.
and merge them. Now this way the time complexity is n by 4k into log 4k log 4k, 4k log k, and this is n log k. So sorting can be done in n log k.
One.
Just the extra steps required are this merging steps. That will be of order n.
What is the time complexity is coming now?
This is and total time complexity. Given any array to get to the final, it is n log n.
No. How?
This is from key sort array to sort array.
Sort. Given a stage, then you are.
This last algorithm is for given any sorted array, k sort array, we
N log k.
that in their time complexity is n log n. And for early algorithms it was.
But can you do little additional work?
What, sir?
The given 2 k sorted arrays, I want to merge it to get 1 k sorted.
That they did it.
Huh?
They themselves did it. It's using parallel computing.
Merging particular.
Yeah.
But
They are
the
doing
value
it.
of k into like from
No,
given
no,
k,
no.
it was the same.
Yeah.
None of the, the merging is there, sorting is there, and getting k sorted.
They mentioned it in the paper how they're going to merge the case sorted out. Any questions?
You ask questions.
Any questions?
Just sitting idle is not a good thing. You should ask someone.
My name is Amit Raj. My roll number is Y2157050. And slow. Y2157050. And my topic is, parallelization of sparse BLAS on shared memory model. And I'm not only, parallelizing, but analyzing, different techniques. How to, how to get an optimal parallelization of sparse BLAS. First of all, before starting, we should understand what is BLAS. What is BLAS and how we will parallelize it, on what model we have to parallelize. So, BLAS is basically a linear algebra subroutines. BLAS is basically a library which provides some functions to do some calculations in like linear system of equation, eigenvalue problem or singular value problem. So there are some library routines which in the BLAS. These library routines are basically of some, like they provide dot products, they provide vector products, they provide matrix vector product, matrix product. So these type of routines are already available in the BLAS, and the benefit with the BLAS is that this is very structured. This is very well documentation is provided. It is very structured. So yeah. So in BLAS, it basically has divides its routine into 3 levels. First level is sparse dot product, vector update, gather and scatter. Level 2 is sparse matrix vector multiply and triangular solve, and level 3 is dense matrix multiply and triangular solve with multiple right hand sides. So I am basically trying to emphasize on level 3 routines, and in level 3 I am emphasizing on matrix product. So this was the BLAS, and now I have to parallelize the BLAS on shared memory model. For shared memory model, I have used OpenMP. OpenMP is basically a library used for multi-threaded shared memory parallelism. It basically works like this: a master thread is forked into some child threads, and then when the parallelism ends, or the parallel region ends, it just joins and the master thread work as sequentially. So master thread always works sequentially, and it just creates some threads by fork when the parallel region start, and then it joins. So the benefit with the OpenMP is that it provides some pragmas. You don't need to take care of the communication between the threads. You don't need to take care of synchronization. Everything is already there. It has implicit barriers. It has implicit communications. So you don't need to go inside the parallelism. You can just write the pragmas for the parallelism, and it's done. So this is the OpenMP. And how it works, I mean, this is shared memory. Here are the processors. They can talk to shared memory through a wire bus, and they itself has some cache. All threads have access to the same globally shared memory. Data can be shared or private. You can define which data should be private, which data should be shared through OpenMP pragmas and some clauses. So private data can be accessed only by threads. Data transfer is transparent to the programmer. This is the best thing for while using the OpenMP. You don't need to take care of the data transfer. It's done automatically. So a simple parallel structure is
What is data transfer?
Data transfer.
Shared memory.
Data transfer. I mean communication between this processor and this shared memory, and even between the threads. So simple. This parallel structures looks like hash pragma OMP parallel and some clauses. So this is the region for parallel code, and what we are doing is basically I'm doing matrix product, and first of all I store the matrix into a compressed structure row format, and then do a sequential multiplication, and then parallelize the multiplication through OpenMP. So what is CSR format? Compressed structure format. So sparse matrix have a lot of entries as zeros. Around a sparse matrix is has at least less than 1/3 entries non-zero. So that matrix can be assumed as a sparse matrix. So the easiest representation of sparse matrix is CSR format. So I am storing a matrix, given matrix, into 3 arrays. The 3 arrays are value array, row array, and column array. So assume like this is a matrix. So it has some entries. How this entries will be stored in 3 arrays? Like values will store what are the actual values, and the row and column will store their indexes. I mean, see, if value 1 is at 0 0 coordinate, so row will be 0, column will be 0. 2 is at row 1 and column 0. So for 2, row will be 1 and column will be 0. So this is how I am storing the sparse matrix into these 3 arrays. It basically reduces the size. It reduces the memory space needed to store sparse matrix. So sequential multiplication given in the BLAS is like you just take the matrix and multiply with the column of B matrix. Then multiplication of this and this will give you a column, and this matrix multiplied by this matrix, which in turn calls this row is multiplied with this column, and then it will give a one entry. So when a matrix multiplied with a column, it gives a one column of C. So this is how matrix multiplied with this column gives one column, this matrix multiplied with this column gives another column. So this is how the columns are generated. So parallel algorithm, assume P processor. So basic two things are matrix multiplied with column, which in turn calls the row and column dot product of row and column. So these are the basic two steps involved in the matrix multiplication. So one thing is either parallelize this portion matrix into column product, or parallelize this row column dot product, or you just parallelize the whole thing. So there are three possibilities of parallelization. So I tested all the three possibilities here. Okay, so this is the first thing. In this I named it P1 algorithm. P1 algorithm is in which a processor will take the matrix and a column and multiply. So the parallelization is at this step, matrix into column multiplication. So P1 is the matrix into column multiplication parallelization. P2 is row and column dot product. So row and column will be multiplied in one processor. So row column will multiplied on a single processor. This is I named it as P2. And another option was that this parallelize matrix into column multiplication. Okay, so matrix and one column will go to one thread, matrix and another column will go to another thread, matrix and another column will go to another thread, and after that one thread will divide into sub threads and then multiply the row and column. So this was another option with me. So I named it P3. So now I will evaluate all these P1, P2, P3 algorithms. I checked above 5,000 because less than
5,000 is a random sparse matrix.
How
did you get from matrix?
matrixmarket.com.
From there you have taken and they are sparse.
Yeah, they are sparse. So I don't know whether they are random or not. But the B matrix, I taken it as random. So for 5,000 cross 5,000, no difference. For 10,000 cross 10,000, this is for P3. P3 was this. P3 was this parallelization at two steps. Okay. So for this thing, I checked for 10,000 cross 10,000 and number of threads and time. This 6 seconds, 5 seconds, and 7 seconds for 4 number of threads, and I didn't write for sequential. Okay.
So why did time increase when you increase the number of threads?
Because see, in OpenMP it is very important to check out the exact the optimal number of threads, because when you create number of threads, it takes some due to communication and thread creation and thread destroy, it takes a lot of time. Okay, and at the synchronization some threads are waiting for another threads. Okay, so if you unnecessarily create some extra threads, it will take extra time. So it's not always necessary that you just create 10 threads for 100 cross 100 matrix. It will give you good time. It can take more time. So this is for around 14,000 cross 14,000, the time was 150. So yeah.
Why this number is such a
So
13,965?
because I found it on the site. I can't change even this number. What? So I mean it is around 14,000 cross 14,000. Yeah, I mean it's like sequential. Yeah, of course. I mean it's almost this difference is, I mean, when you do some more iteration, it will give you 125. It may give you 115. Okay.
No, but what you can you compute? What is the conclusion from this?
What is the difference between sequential and one number of threads?
I mean, they are almost same.
Almost one?
I mean, they are same.
Why is time difference of 10 seconds?
10 seconds is a lot. I mean, if you say
10
milliseconds it's a different thing. 10 seconds is a lot.
Why 10 seconds?
Even I mean,
And even
I tested it.
Time should be more because you are creating a
Yes.
Sorry, what?
You're creating a thread and destroying it. So time should be more different.
Yeah, I mean,
Sequential and one.
but I mean, I don't know why.
Unless once, or have you taken the average?
Taken the average of 3 iterations. So I just
Maybe you
take,
should have gone for more iterations than you would have got better.
maybe.
But you have done on the same sparse pattern.
Same sparse matrix. Yes. So even, I mean, sometimes the results were very different. I mean, in the morning you take some other. So because I mean, really, I mean, I look. Yeah, in CSE lab.
That's why.
In CSE lab.
Is it a temperature dependent or?
No, actually it depends on the process, number of users.
No, but then you take the standard machine.
So, but I done it at the CSE machines.
You take standard machine.
People keep using CP and
That's why
that is
No, no,
That's
no.
it.
If you want to separate out from the net and you make your internal network and
I mean,
Without the land.
no, that is not a correct way of viewing. This is the useless type.
no, I mean,
you cannot show.
so that was the problem with me. I mean, because I mean, it depends on the number of users connected to this computer or the process connected.
Once you are showing this time should be your time, right? You know, who are the other users using it, then this time is useless time. It is another time it is meaning.
This is the problem, sir.
This is not problem. You ask VM Shukla, he will give you. You have to, no, that is, you go there and ask him that I want 4 machines for 5 days, he will give you.
So I mean, he just say what is OpenMP and he don't know anything. He speak very rudely, sir.
No, just removing it.
So he may need, do you need root password also?
Yeah, of course, I need the root password.
But this time is another. You tell PM Shukla, and if you need, I can also talk to you.
Yes, that would.
How many machines you need?
I mean, one machine.
One machine only. So you will be creating thread, right? So you have laptop instead of it.
Yeah, I mean, but I don't have OpenMP.
OpenMP is open source.
Yeah, open.
That is.
So I mean, you just look up further. We can have some conclusion. So, I mean,
No, here. See, there is another problem. Here, your problem is more complex. See, sequential, you take 118,
yeah,
1 thread 115, 2 threads 110.
110.
And
Are you using dual core or single?
I don't know. It was dual core. I don't know.
Because in dual core, if you create
I mean,
thread, then
because that is not a dual core. I think CSE machine, this machines are not dual core.
no, listen machines are
The black ones are dual core.
The Dell machines.
But
listen
Dell machines are not.
listen machines are dual.
yeah, black one.
I don't know whether black, white, right? This is called.
Dell
Dell
one.
ones are separate.
So your program is ready, right?
Yeah.
So what you have to do, you need a machine
Yeah.
to test it. You do that.
Okay, so these are the some readings which I got.
That you have problem.
Sir, so there is one system CSC ITSRV with 4 cores. You can test it.
We use four number of threads.
Anyway, he is also doing 4 thread, right?
Yeah.
So he should get a gain of around 4 in that if he is using 4 cores.
But don't BLAS take care of the 4 cores process?
What?
Doesn't BLAS take care of the 4 core itself? BLAS will automatically.
Automatically. BLAS does automatically.
Yeah. If you install BLAS, BLAS will consider that processor is dual core or single processor.
You mean BLAS or OpenMP?
OpenMP should depend.
We are doing BLAS or OpenMP.
I mean, BLAS is the routine.
BLAS is the routine.
BLAS is
And in that routine, automatically it finds out the number of processors and it decides. That is the BLAS job, right? And he optimizes the thing. Now, if you use OpenMP, you can control the number of processors you are using. Isn't it?
So it would be, I mean, better if I take.
What is better? But this analysis are no good.
Yeah, I mean, because it is in effect with some other process.
So that because I have to do a lot of things.
So I mean, anyway, whatever the readings from that readings, what I.
This competition reduces. These are all useless for you.
Why?
Yours is not the this. Your thing is implementation thing, right?
Yeah.
So you should tell on this model, on this machine, if you use 4 thread, this is the result. Like the time it should be in terms of time.
Yeah.
Not on this because you cannot draw such type of conclusion.
I mean, we can reduce because I mean, whatever is the number of non-zeros, only non-zeros numbers will multiplied with the B matrix. Zeros will not be multiplied. So instead of this n cube, I think, sorry, that should be n square. So non-zeros numbers only multiplied with the B matrix. So that's why the computation.
Try to see this one. I have a lot of doubt. If computational reduction is parallel computational reduction. What is computational?
I mean, from sequential, n cube is the sequential. Okay, and now when you go to the parallel ones, sorry, then it reduces by p.
See, sparse matrix multiplication algorithm cannot take n cube time.
Yeah, I mean, yeah, this should also be nz into p, nz into n. Sorry.
See, in one side you are comparing with sparse matrix.
This side is this side.
Matrix.
This should be nz into n.
I don't know. This is you have to find out.
So anyway, I mean, from whatever the results that we got from those things, I just conclude that P1 seems be the best. I mean, P1, this parallelization seems best because.
How is that possible? P3 you are doing P1 and P2 both.
Yeah, but the threads are creating a lot of. I mean, one thread is creating, then 4 threads are creating, then.
It means that you didn't do the dynamic load balancing.
Dynamic load balancing.
Because if you do dynamic load balancing, then the time should be like of the order of the number of processes. Because you are doing matrix multiplication, it is more computation intensive.
Yeah. So maybe I don't do load balancing.
So what is telling that are you dividing the number of based on number of non-zero elements?
Yes.
Or based on the row and column?
Based on number of non-zeros.
Then equal number of non-zero elements you are allocating to each thread?
Equal number of. So the number of non-zeros.
If you use the row and column, then what is the why you are representing non-zero elements?
So actually, this is the routines given in the BLAS. I can't do anything. I can't change.
Why? The routines
I
are
mean,
available now.
yeah, I can change, but I am parallelizing the BLAS. So I mean, there should be BLAS. I can't put my Strasson's algorithm in BLAS. So the BLAS algorithms I can't change. Otherwise, it won't be BLAS. That's why. And BLAS is taking row and multiplying with column. So if I parallelize with row and column, then it may have, I mean, one row can have 2 or 3 non-zero elements.
Then why you are representing RCB form?
RCP?
CSR
form.
CSR form.
That is only to store, I mean, big matrix to store in the hard disk. I mean, otherwise it will take a lot of space. And when it will multiply, it will just 3 arrays are passed and corresponding entries are passed. I can show you the code. Then, I mean,
No, that anyway you have to show.
Yeah.
Well, you are feeling that you will not show me?
No. I can show you the demo right now.
Demo will not give you the demo on your laptop.
No, on the CSC machine through SSH.
No, now you implement it on the 4 machines.
Okay, yeah.
And then show.
Yeah, I mean,
When
basically run on.
When are you showing me all the things?
Just 23rd, 24th.
You could have done dynamic scheduling just while you adding the breakmarks of OpenMP, just you add the clause schedule dynamic.
Schedule dynamic.
I think it will take care of all this.
Okay.
There are different row sizes.
Actually, I was looking at. That will do load balancing also?
Yeah.
Okay.
But not at this level. I think P2 will be, P2 or P3 will be better in that case.
Okay.
Check it.
Yeah.
Note down all the suggestions.
Yes.
Any other suggestions you want to give him?
Any other solutions?